The Roman Space Telescope. NASA's next great observatory is about to launch. It will see more of the universe in a single image than Hubble has seen in 30 years. This is the story of humanity's most ambitious eye on the cosmos. Named after Nancy Grace Roman, NASA's first chief of astronomy, this telescope carries a legacy that spans decades. She was known as the Mother of Hubble. Without her tireless advocacy, the Hubble Space Telescope might never have been built. Now her namesake will surpass everything that came before. The telescope was completed in November 2025 after years of careful construction at the Goddard Space Flight Center. After extensive testing, it sits ready for launch from Cape Canaveral. The target date is August 30, 2026. A SpaceX Falcon Heavy rocket will carry it to a point 1 million miles from Earth. That point is called Lagrange Point 2, or L2. It is a gravitationally stable spot where the telescope can orbit the Sun while staying aligned with Earth. The James Webb Space Telescope is already there, observing the first galaxies that formed after the Big Bang. Soon Roman will join it. Together they will observe the universe in ways that were impossible just a decade ago. Webb sees deep and narrow. Roman sees wide and fast. They are the perfect pair. Roman's primary mirror is 2.4 meters wide. That is the same size as Hubble's mirror. But Roman is not a copy of Hubble. Its real power comes from its enormous field of view. Roman's wide field instrument captures an area of sky 100 times larger than Hubble's infrared camera. It will take just 1 year to map more of the universe than Hubble has mapped in its entire 30-year lifetime. That is not an exaggeration. The numbers are built into the design. Each Roman image will cover an area of sky the size of 70 full moons. The telescope will produce 200 times more data than Hubble in the same amount of time. Roman is a survey telescope. It is built to scan vast areas of sky quickly and deeply. Where Hubble studies individual objects in exquisite detail, Roman will capture entire populations of galaxies, stars, and planets in a single frame. The science goals are divided into two main areas: dark energy and exoplanets. These are the two biggest questions in modern astronomy. What is accelerating the expansion of the universe? And are we alone in the galaxy? Roman will provide answers to both. Dark energy is the name given to the mysterious force driving the universe to expand faster and faster. It was discovered in 1998 and it completely changed our understanding of cosmology. Before that, scientists believed the expansion of the universe was slowing down due to gravity. The discovery that it was accelerating won the Nobel Prize. But we still do not know what dark energy actually is. It makes up about 70% of the universe, yet it remains completely invisible to us. Roman will use 3 different methods to study dark energy: baryon acoustic oscillations, distant supernovae, and weak gravitational lensing. Each method is independent. Each provides a cross-check on the others. If they all agree, we can be confident in the results. Baryon acoustic oscillations are ripples in the distribution of matter across the universe. They were imprinted just 400,000 years after the Big Bang, when the universe was still a hot plasma. Sound waves traveled through this plasma, creating regular patterns of density. When the universe cooled, these patterns were frozen into the distribution of galaxies. By measuring these ripples at different distances, Roman can trace how the expansion rate of the universe has changed over time. This reveals the behavior of dark energy across cosmic history. Distant supernovae act as standard candles. Type Ia supernovae explode with a known intrinsic brightness. By measuring how dim they appear from Earth, astronomers can calculate how far away they are and how much the universe has expanded since the light left them. Roman will find thousands of these supernovae across billions of years of cosmic time. It will see them at distances that are difficult for ground-based telescopes to reach. Weak gravitational lensing is perhaps the most elegant technique. Massive objects like galaxies bend the fabric of spacetime. Light traveling past them is distorted, like looking through a warped lens. By measuring these distortions across millions of galaxies, astronomers can map the distribution of dark matter and study how cosmic structures have grown over time. This growth is directly affected by dark energy. The results will tell us whether dark energy is a constant force or something that changes over time. The second major science goal is exoplanets. Roman will use a technique called microlensing. When a foreground star passes in front of a background star, the foreground star's gravity bends the light from the background star, magnifying it. If the foreground star has planets, those planets create additional distortions in the magnification. It is a beautiful effect predicted by Einstein's theory of general relativity. Microlensing is the only way to find planets that are far from their host stars. It can detect planets as small as Mars. It can find planets in the outer regions of solar systems where our other methods cannot see. The Kepler mission found thousands of planets close to their stars. Roman will find the ones farther out, in the cold outer regions where our own solar system's gas giants reside. Roman is expected to discover thousands of new exoplanets. Some of them may be Earth-sized. Some may be in the habitable zones of their stars. The microlensing survey will give us the first complete census of planetary systems across the galaxy. We will finally know how common Earth-like planets really are. The telescope also carries a technology demonstration. The coronagraph instrument. This is a device that blocks the light from a star to reveal the planets orbiting around it. It is incredibly difficult because a star is billions of times brighter than its planets. The coronagraph uses advanced optics to cancel out the starlight with extreme precision. Tiny deformable mirrors with thousands of actuators shape the light to create a dark hole where planets can be seen. If successful, the Roman coronagraph will be the first step toward directly imaging Earth-like planets around other stars. Future missions like the Habitable Worlds Observatory will build on this technology. We are witnessing the beginning of a new era in exoplanet science. The first direct image of an Earth-like planet may come within our lifetime. The coronagraph is a critical stepping stone toward that goal. It will demonstrate technologies that future missions will rely on for decades to come. The High-Latitude Wide Area Survey is another key component of Roman's mission. It will observe large areas of sky at high galactic latitudes, away from the dust and stars of the Milky Way's disk. This survey will capture hundreds of millions of galaxies. It will create the largest three-dimensional map of the universe ever made. Cosmologists will use this map to study the large-scale structure of the cosmos and test theories of gravity on the largest scales. Roman will also conduct a galactic bulge time domain survey. This survey will repeatedly observe the crowded center of the Milky Way, looking for microlensing events and other transient phenomena. The galactic bulge is a dense region of stars where the chance of a microlensing alignment is highest. Roman will watch this region every 15 minutes for months at a time. It will detect not only exoplanets but also isolated black holes, neutron stars, and other exotic objects that are otherwise invisible. The telescope will also study the evolution of galaxies across cosmic time. By observing hundreds of thousands of galaxies at different distances, Roman will trace how galaxies grow, merge, and change over billions of years. It will see how supermassive black holes at the centers of galaxies influence their surroundings. It will witness the cosmic web of dark matter that connects galaxies across the universe. Roman's survey of nearby galaxies will provide new insights into star formation. It will observe the infrared light from young stars still embedded in their birth clouds. This will reveal the rate of star formation in different types of galaxies and how it has changed over time. The data will be invaluable for understanding the life cycle of galaxies. The mission is designed to last at least 5 years, but the fuel supply could allow it to operate for 10 years or more. Like Hubble and Webb, Roman could far exceed its planned lifetime. Every additional year of operation means more data, more discoveries, and more opportunities for the global scientific community. The Roman Space Telescope represents a new way of doing astronomy. It is not just a telescope for a select few. It is a facility for the entire world. The data will be open and accessible. The tools will be public. The discoveries will belong to everyone. This is the democratization of space science at its finest. Roman's data will be massive. It will generate 11 terabytes of data per day. That is more than any NASA astrophysics mission before it. To handle this, the team has built a sophisticated data pipeline. The data will be processed at the Space Telescope Science Institute in Baltimore and made publicly available immediately. There is no proprietary period. Anyone in the world can access it the moment it arrives. A student in a developing country can discover a new exoplanet on the same day as a professor at Harvard. The Roman Space Telescope is also a time machine. Because it looks at distant objects, it sees them as they were billions of years ago. Light from the most distant galaxies takes billions of years to reach us. Roman will see galaxies as they were when the universe was less than 1 billion years old. It will watch the formation of the first stars and galaxies, filling in a critical gap in our cosmic history. The Wide Field Instrument operates in the near-infrared. This is crucial because the light from the most distant galaxies has been stretched by the expansion of the universe into infrared wavelengths. Roman can see what Hubble cannot. It can peer through dust clouds that block visible light. It can see the birthplaces of stars and planets hidden inside dense molecular clouds. The telescope's design is based on hardware donated by the National Reconnaissance Office. In 2012, the NRO gave NASA 2 unused spy satellite telescopes that were originally built for surveillance. These telescopes were repurposed for astronomy. This collaboration between intelligence and science saved billions of dollars and accelerated the mission by years. It is one of the most remarkable partnerships in the history of space exploration. When Roman begins its survey in late 2026, it will transform our understanding of the universe. We will see the distribution of dark matter in unprecedented detail. We will find planets we never knew existed. We will watch the universe expand in real time across billions of years. The Roman Space Telescope is not just a telescope. It is a time machine, a planet hunter, and a dark energy detective. It is the next great observatory. And it is launching soon.